Good afternoon, students. Welcome back once again to the mathematics class. In the last class, we have solved some standard functions, that is, derivative of some standard functions. We have solved sin x, cos x, tan x, cot x, sec x, cosec x, e to the power of x, log x, e to the power of x, root x, 1 by x. These are all standard functions. We have solved its derivative by using first principle. Next, let's see some examples based on these standard functions. So the first example of this lecture: differentiate root x with respect to x from first principle. First principles, right? So let's see. By using first principle method, we can find the differentiation of root x. So solution: let write down the given function f of x equals to root x. So already we have standard form, that is f dash of x, which is equals to limit h tends to 0, that is root under root of x plus h minus root x whole divided by h, and limit h tends to 0. Rationalizing, so we can write it here: x plus h minus x divided by root x plus h plus of root x. Rationalizing the numerator. Rationalizing the numerator. So we can write it here: limit h tends to 0, 1 upon under root of x plus h plus root x, which is equals to, so here minus x plus x get cancelled, h also get cancelled. What we get remaining we have written here, so which is equals to 1 upon, when h tends to 0, what we get? Root x. Root x is nothing but 2 times of root x. Therefore, hence d by dx of root x, which is equals to 1 upon 2 root x. Got it? So next, one more example we will see here. This is example 2. Differentiate ax square plus bx plus c with respect to x from first principle. Let's say solution for this one. First write down, let f of x the given function ax square plus bx plus c. So now f dash of x can be written as limit h tends to 0, a x plus h whole square plus b x plus h plus c minus of ax square plus bx plus c whole divided by h. Limit h tends to 0, a as it is. Now expanding a plus b whole square form, that is a square plus 2ab plus b square plus of x plus h plus c minus of ax square bx plus of c over divided by h, right? So limit h tends to 0. Now multiply inside ax square plus 2ahx plus ah square plus bx plus bh plus c minus ax square minus bx minus c all divided by h. So now limit h tends to 0. Here plus ax square minus ax square get cancelled. H taking outside 2ax plus bx minus bx plus c minus c. These are get cancelled. Now remaining terms ah square means only what we have here ah plus of b divided by h, right? Here h get cancelled. What we get 2ax plus b plus 0 when apply h tends to 0 which is equals to 2x which is equals to what we get 2ax plus of b, that is nothing but d by dx of what ax square plus bx plus c which is equals to 2ax plus b is nothing but the differentiation of ax square plus bx plus c. Next third one, differentiate sine ax with respect to x from first principle. Solution. So let f of x equals to sine ax, then f dash of x which is equals to limit x tends to 0 sine a x plus h sine ax all divided by h which is equals to limit h tends to 0 2 cos of ax plus ah plus ax all divided by 2 sine of ax plus ah minus ax by 2 all divided by h. So limit h tends to 0 2 cos of which can be written as ax plus ah by 2 sine of ah by 2 is plus x minus ax get cancelled. So remaining we can write it here limit h tends to 0 all divided by as it is here. So 2 cos of ax plus ah by 2 into sin ah by 2 divided by h is there. So now limit h tends to 0 2 cos of ax plus ah by 2 sin ah by 2 divided by ah by 2 into a by 2. So just multiplying and dividing by a by 2 here. So now applying limit h tends to 0, what we get? 2 times of cos ax plus of 0 into 1 into a by 2. So f dash of x a cos ax. Got it? It is differentiation of sin x is cos x. So here again differentiating ax, what we get? A is a constant term here, we get a. Similarly, next example you will see example number 4. Find the derivative of ax plus b cx plus d with respect to x on first principle. It is f of x equals to ax plus b cx plus d. So hence f dash of x, which is equals to limit h tends to 0 a into x plus h plus of b divided by c into x plus h plus of d minus ax plus b divided by cx plus b. Just when substituting in the standard form, whole divided by h. So now limit h tends to 0 a into x plus h plus of b into cx plus d minus c into x plus h d into ax plus b whole divided by h, right? Just cross multiply here. Just by cross multiplying, remaining write down as it is here h into c into x plus h plus d cx plus d, right? So remaining we can write it as it is here. Limit h tends to 0 ad minus bc. The terms get cancelled here. Remaining, after cancelling the remaining terms, what we can write? So what we can write here? Cx plus h d. So by taking ad minus bc, ad minus of bc into h divided by cx plus h plus of d cx plus of d. So ad minus by h get cancelled. ad minus bc divided by c into x plus 0 plus d cx plus of d. So which is equals to, we can write it as ad minus bc whole divided by cx plus d whole square. So here it becomes cx plus d whole square. Here the term, just multiply and simplify this, what we'll get here? ad minus of bc. After simplifying we get ad minus of bc. So here the derivative of ax plus b by cx plus d is nothing but ad minus bc by cx plus d whole square. Next, fifth one, differentiate sine square x with respect to x from first principle. So solution f of x, which is equals to sine square x, hence f dash of x, which is equals to limit h tends to 0 sine square of x plus h minus sine square x whole divided by h. So limit h tends to 0 sine of x plus h plus of x sine of x plus h minus of x divided by h, since sine square a minus sine square b, which is equals to sine a plus b sine a minus b. So we can write it here. Limit h tends to 0 sine of 2x plus h into sine h by h. So now which can be written as limit h tends to 0 sine 2x plus 0 into 1. So sine 2x, which is equals to 2 sine x into cos x, is nothing but derivative of sine square x, that is nothing but 2 sine x into cos x. So with this we will conclude our today's lecture. In the next lecture we will see rules of differentiation. So till then, take care, stay at home, stay safe. Thank you.